Okay. So, uh, yeah, let's get on with the class. So, it's again another class of mechanical operations. And I think last class we were talking or briefly going through topics of screening and size reduction. And first of all, just can someone confirm whether I'm audible or not? Hello. Okay. So yeah, so we were looking into mechanical operations. So we were so far we have covered size reduction equipment, screening, sieving, and I think a brief part of cyclone separator and so on. So today we'll be looking into a different topic in the same mechanical operations itself. We'll be looking into something called as solid liquid separation, or this is also you can say sedimentation, right? So sedimentation, I'm pretty sure everyone knows what sedimentation is. So, for example, you have a glass, let's say, and let's say you have water filled in the glass, and you put in some sugar cubes or some sugar crystals from the top. Eventually, this will sink into the water, and it will start you know collecting at the bottom. This is like the very rough or layman definition of sedimentation that we see, in everyday life of ours. So sedimentation, the proper definition of sedimentation is the separation of solids from suspension in liquid by gravity. So this sedimentation or the sinking of these sugar crystals occur because of gravity. So this is the basic definition of sedimentation, and you can also call this as settling of particles. So in mechanical operations, we'll be going through two types of settling. So one is called the free settling, and the other is called hindered settling. So in free settling, this settling is affected only by gravity. So when you do the force balance, the only forces that will be having a major effect on the settling in free settling is gravity. And of course, because it is a solid in which is sinking in liquid, you will also have buoyancy forces, and that is applicable for both the free settling as well as hindered settling. You'll have buoyancy forces as well as drag forces. So we'll be looking into these things a bit more in the detail in the coming sections. But this is the key point here. The external force in a free settling is only gravity. But in hindered settling, there will be more forces that will be acting on the your settling of the particles. So for example, um, you know, this can be affected by the presence of other particles. So for example, if you are put in the same water, sugar in water example, if you are putting too much of sugar in the water, one sugar crystal may affect the settling of the sugar crystal on top of this sugar crystal. So let's say this shaded sugar crystal is settling very slowly because of some factor, whatever. The sugar crystal on top of it will also be affected by this slow settling sugar crystal. So this is one example of hindered settling. So other factors can also affect the settling here. So these two are the different types of settling that we will be encountering in mechanical operations. So let us first start with free settling. Right. So let us take an example. So let us say we have a vessel like this, and the vessel is filled with water, or it can be any fluid, but for our simplicity, we'll take it as water. And you have only one particle that is trying to settle to the bottom of this vessel through the water medium. Now, if you take this particle, there are a lot of forces that will be acting on it. And the first force is the gravitational force. Then you have the buoyancy force that is acting opposite to this. So buoyancy force will try to bring this particle to the top, while the gravity will try to bring this particle to the bottom of the vessel. And because there is movement of this particle inside or through this water medium, there will be, of course, a drag force on the surface. So the three forces acting here are buoyancy, which is acting in the top direction or the upward direction. Then there is gravity, which is acting in the downward direction. And then there is drag, drag force, which is also acting in the upward direction. Now, if we consider equilibrium, let's say this particle is stationary like this, and not stationary, I would say. Um, let us, before we consider equilibrium, let us try to see what the force balance equation will look like. So, you know, net force will be consisting of these three forces that we are, considering. So, net force will be equal to gravity minus buoyancy, because these are in the opposite directions, minus drag force. So net force, you can write it as M into A by Newton's laws. So F is equal to ma, right? So net force, you can write it as ma, which is equal to gravity. You can write gravity as mg, and the buoyancy force, you can write it as fb, and then the drag force, you can write it as fd. Now, by Archimedes' principle, you must have learned it also. Buoyancy force Fb, you can write it as rho into V into G. This is also like the yeah. This is the according to the Archimedes principle that we must have learned during our school times. So buoyancy is rho, which is the density, into V, which is the volume, and G. So this rho is basically rho F. This F means fluid, water. So rho F is the density of water. So you can take this rho F in terms of any fluid in consideration. Here we are taking it as water. So the rho F is the density of water. V, it's actually volume of the particle. So we will represent it as Vp. And G is the gravity. So you can rewrite this as rho F into volume. Volume you can write it as mass by density. So you can write it as mp by rho p into G. Right. Now the other force in consideration, drag force, you must have learned this in fluid mechanics. You can write drag force as CD into rho F v square. This is small v, which is the velocity, into area of the particle. We'll take it as AP by 2. So this is something you will probably have learned in fluid mechanics with regards to the equation of drag force. So here this CD is the coefficient of drag force, or coefficient of drag coefficient. You can say it like that. Then rho F is the density of the fluid. V square is the velocity of the particle. AP is the area of the particle. Now what we have to do is we will substitute these two forces FD and FB in this force balance equation. So, and also one more thing we can write here, this acceleration term here. This A, you can write it as dv by dt. Right? Acceleration is basically the time derivative of velocity. So now we'll substitute all these things in this force balance. We can get m into dv by dt is equal to mg minus m into rho f by rho p. This m is basically mass of particle, mp. So we are just taking it as m for simplicity sake. So rho f into rho p into g minus cd rho f v square ap by 2. Now there is one term called as terminal settling velocity. So this is what we are trying to find here in this free settling. So at terminal settling velocity, the acceleration of the particle will be 0, or the particle that is settling will be at a constant velocity. So in other words, dv by dt will be 0. So that means this term will be 0. And this we'll get this force balance equation at terminal settling velocity as 0 is equal to mg minus m into rho f minus by rho p into g minus cd rho f v square ap by 2. So this will become our force balance at free settling velocity, and free settling velocity is where the acceleration of the particle is 0. That means that particle is settling at a constant velocity, and this constant velocity is the maximum velocity at which this particle can settle in that given situation. Right. Now if we solve this equation, we can get the term for velocity v, which we can term it as terminal settling velocity ut. So we'll represent the terminal settling velocity as u in ut. So this ut will be equal to root of 2m rho p minus rho f into g by cd ap rho P, rho F, where rho P means the density of the particle and rho F means density of the fluid. And then M is the mass of the particle, CD is the drag coefficient, and G is the gravity. Right? So this is the general equation for terminal settling velocity for any situation. Now we'll be looking into a specific case where we'll assume our particle is spherical. So the settling particle that we have, we'll assume it as a spherical particle. So for spherical particle, we have a lot of equations for the volume and area. Now what we'll try to do here is we have the mass of the particle, and this mass is basically rho p by Vp, or density by volume. You mean this slide? Okay. So this mass, we'll try to write it as density by volume. And because it is a sphere, the volume of the particle will be 4 by 3 into pi dp by 2 the whole cube. Right, 4 by 3 pi r square. So here dp is the diameter of the particle. So what we'll do is we'll try to substitute this m in our equation, and we'll get a general equation for spherical particle as ut is equal to root of 4 dp into rho p minus rho f by 3 cd rho f. Oh, also one more thing what we try to do here is, because it is the spherical particle, the area of the particle will be 4 pi dp by 2 the whole square. So we substituted these two terms for the mass of the particle and area of the particle, and after simplifying it, we will get the equation for spherical particle like this, which is ut, the terminal velocity, which is equal to root of 4 dp into rho p minus rho f by 3 cd rho f. So once you have noted this, there are three cases here that we will try to account for. The first case is at very low Reynolds number, and that is also called as Stokes regime. Then the other extreme, which is very high Reynolds number, and that is called as Newton's regime. And then there is obviously there will be one that will be in the intermediate range. So intermediate Reynolds number will be something like 1 to 1000. This is called as intermediate regime. So in Stokes regime, the Reynolds number is usually less than 1. And in Newton's regime, the Reynolds number is usually greater than 1000. So the other peculiar thing that you can notice here is the Stokes regime, the flow will be laminar. And in the Newton's regime, the flow can become turbulent. Not always, but there is a higher probability of this becoming turbulent. And in the intermediate region, it will be mostly in the transitional flow phase. Right. So now, okay, just take a note of this, and we'll try to see how this equation changes with respect to each of these regimes. Okay. So first, let's start with Stokes regime. So in Stokes regime, the Reynolds number is less than 1, and for such low Reynolds number, you can approximate the drag coefficient CD as 24 by RE, or 24 by Reynolds number. Okay, and by definition, this Reynolds number is rho P into dP into V by mu P, mu F, right? Where rho P is the density of the particle, dP is the diameter of the particle, V, which is basically ut, the terminal settling velocity. V is terminal settling velocity, and mu F is the viscosity of the fluid. So now substituting this, we'll get CD is equal to 24 into mu F by rho P dP into ut. Now what we'll do is we'll try to substitute this CD in our general equation for spherical particles, which is ut is equal to root of 4 dP into rho P minus rho F into G by 3 CD rho F. And what we'll do, once we substitute it, we'll get something like 4 dP into rho P minus rho F into G into rho P dP ut, the whole by 3 into 24 mu F into rho F. Just substituting this. Now if we simplify it and try to bring this ut from inside the root to the left hand side and do some simplifications and all that, we can get the terminal velocity equation as ut is equal to g dP square into rho P minus rho F by 18 mu F. So this is the terminal settling velocity for Stokes regime. Right. So yeah, if you have noted it, we'll move to the next regime, which is the Newton's regime. So in the Newton's regime, the Reynolds number usually sits in the range of 1000 to 2 into 10 raised to 5. And in this case, we can approximate this coefficient of drag CD as 0.44. So what we'll do is we'll do the same thing. We'll substitute this CD in our equation for terminal settling velocity, and it will become 3 dp rho p minus rho f into g by rho f. So what we did, basically we just substituted this CD in this general equation here for this CD as 0.44, and we just simplified it, and we'll get our equation for terminal settling velocity for Newton's regime like this. Right. So these two are the two important regimes that we need to consider for mechanical operations. And of course, for intermediate regime, usually this is not really considered for questions when it just comes to gate. But for the knowledge sake, you can write this intermediate regime as basically as a combination of both Stokes regime and Newton's regime. So here you can approximate this CD as 24 by RE plus 0.44. So based on your requirements, you can just substitute the value of CD from whichever range that you want in the general equation, and you can find the equation for that corresponding regime. Right? Fine. So let's quickly just move to hindered settling as well before we start solving the problems. So hindered settling velocity. So terminal settling velocity, you can also call it as free settling velocity. And in hindered settling also you have a terminal settling velocity, which yeah. So in hindered settling, we'll have the velocity called as hindered settling velocity. This is different from the terminal settling velocity, because terminal settling velocity will only consider free settling. That means the presence of other particle does not affect the settling velocity there. So this is not equal to ut, which is free settling, right? So in terminal settling velocity, so I won't be going through the derivation, I'll just give you the brief equation here. We have an equation for terminal settling velocity as u by ut is equal to epsilon raised to n. So here u is the hindered settling velocity, ut is the free settling velocity or terminal settling velocity, and epsilon is the void fraction or porosity. And you can get epsilon by volume of liquid by volume of suspension. Or another definition for this void fraction is void volume by total volume. So this is epsilon. Then this n is actually a constant. And this constant can have different values based on which regime the settling happens. So for example, n will be equal to 2.39 if the settling is in Newton's regime. And this n will be equal to 4.65 if the settling is in Stokes regime. Right. Okay, fine. So just make a note of these equations. We'll stop with the theoretical part here. We'll try to solve two or three questions today before we conclude. So just go through all these things, and if there are any doubts, you can always ask. I'll give you a minute. If everything is clear, we can move on to the questions. Okay. Um, Fine then. We'll move to the questions. So this is a question from GATE 2016 from Chemical Engineering. Question number 37. Consider a rigid solid sphere falling with a constant velocity in a fluid. The following data are known at the conditions of interest. Viscosity of the fluid is equal to zero point 0.1 Pascal second. Acceleration due to gravity is 10 meter per second square. Density of the particle is 1180 kilogram per meter cube, and density of the fluid is 1000 kilogram per meter cube. The diameter in millimeter rounded off to the second decimal place of the largest sphere that settles in the Stokes law regime, where Reynolds number is less than or equal to zero point 0.1, is dash. So this is a question from terminal settling velocity part in mechanical operations, and the NPTEL lecture can be found in Unit 4, Lecture 16, Particle Dynamics 1, Mechanical Operations by Professor Shabina Khanam, Department of Chemical Engineering, IIT Roorkee. So here in this question, they have given the regime as Stokes regime, and the particle is settling here, and the settling here is a free settling at a constant velocity. So we can write the terminal settling velocity for the Stokes law regime here, which is ut is equal to g dp square rho p minus rho f by 18 mu f, where g is the gravitational force, dp is the diameter of the particle, rho p and rho f are the densities of particle and fluid, and mu f is the viscosity of the fluid. So let us write down the values that is given to us. So our equation, general equation here is ut is equal to g dp square rho p minus rho f by 18 mu f. So here dp is unknown, g is given as 10 meter per second square, rho p is given as 1180 kilogram per meter cube, and rho f is given as 1000 kilogram per meter cube, and mu f, which is the viscosity, is given as zero point 0.1 Pascal second. So let us substitute everything here. in the settling velocity. So ut will be equal to 10 into dp square into rho p, that is 1180, minus rho f, that is 1000, by 18 into mu f, that is 0.1. Now if we simplify this, we'll get ut is equal to 10 into dp square into 180 by 18 into 0.1. So 18 and 180 gets cancelled, and we'll get ut is equal to 1000 dp square. Let us take this as equation number 1. The other data that they have given us here is that the Reynolds number is less than or equal to 0.1 at this condition. So we can approximately take Reynolds number Re is equal to 0.1, and the Reynolds number is equal to rho into d into v by mu, by the general equation for Reynolds number. So here this Reynolds number Re, which is 0.1, will be equal to rho f into dp, which is the diameter of the particle, into velocity of the particle v. And since this is at terminal settling velocity, this velocity will be equal to terminal settling velocity ut. So this will be rho f into dp into ut by mu f. And we have the values for all these things except for dp and ut. So just substitute all these values here. The Reynolds number will be equal to 0.1, which is equal to rho f, that is 1000, into dp into ut by 18, which is mu f. So let us write this again. 0.1 will be equal to 1000 into dp into ut by mu f, which is 0.1. So now from equation 1, we have ut is equal to 1000 dp square from equation 1. So substitute for this ut in this equation 2, we'll get 0.1 is equal to 1000 into dp into 1000 dp square by 0.1. So this is an equation with only dp as the variable. So if we simplify and solve for dp, we can get dp is equal to 0.1 into 0.1 by 1000 into 1000, the whole raised to 1 by 3 meters. And if we do this mathematics, we'll get dp as approximately 2.15 millimeter. So the right answer here in this question is 2.15 millimeters. Right? Okay. So this is basically just a straightforward question, using the Stokes regime of settling. And most of the questions from these are usually straightforward in nature. Mostly direct applications of your settling velocity equations. So if there are no doubts, if you have any doubts, you can always speak up or just type in the chat box. But if there are no doubts, okay, we'll move to the next question. Okay. So this is a question from GATE 2008 from Chemical Engineering. Question number 41. Two identically sized spherical particles A and B having densities rho A and rho B respectively are settling in a fluid of density rho. Assuming free settling under turbulent flow conditions, the ratio of terminal settling velocity of particle A to that of particle B is given by dash, and the four options are given as below. So this is a question from terminal settling velocity from mechanical operations, and the reference NPTEL videos can be found in Unit 4, Lecture 16, Particle Dynamics 1, Mechanical Operations by Professor Shabina Khanam, Department of Chemical Engineering, IIT Roorkee. So in this question, they have said that two identically sized spherical particles, so A and B, having densities rho A and rho B, are settling in a fluid having a density rho. And because these two different particles have different densities, their terminal settling velocity is also expected to be different, and we are having to find the ratio of this terminal settling velocity of particle A to that of particle B. Now, one data that they have given us here is that these two spheres are identical in size. So that means dA, which is the diameter of particle A, will be equal to dB, which is the diameter of the particle B. And another data that they have given is that it is in turbulent mode, or this means it is in Newton's regime. So in Newton's regime, the terminal settling velocity can be written as ut is equal to root of 3 dp into g into rho p minus rho f by rho f, where rho p is the density of particle and rho f is the density of fluid, and dp is the diameter of the particle. So what we'll try here is we'll try to substitute this equation for both the particles A and B. So for particle A, the settling velocity UTA will be root of 3 dA into G into rho A minus rho by rho. Because the particle density here is rho A and the fluid density is rho, and the diameter of particle A is dA. And for particle B, UTB will be equal to root of 3 dB into G into rho B minus rho by rho. So what we have to find here is the ratio of these two settling velocities, which is UTA by UTB, and that will be equal to root of 3 dA into G into rho A minus rho by rho by root of 3 dB into G rho B minus rho by rho. So here both these denominators rho will get cancelled. The constant 3 and G will get cancelled, and dA and dB will also get cancelled because dA is equal to dB here, because A and B are identical in size. So dA and dB will also get cancelled. And then finally, the ratio of the settling velocities UTA by UTB will be root of rho A minus rho by rho B minus rho. So in the option, this is option A. So the right answer for this question is option A, which is root of rho A minus rho by rho B minus rho. Right. So again, this is just another application question. We just applied the Newton's regime equation directly for two particles, just cancelled out all the common terms, and we got the ratio of the terminal settling velocities of particle A and B. Okay. We'll try to solve one more question if there are no doubts with this question. Right. So this is a question from GATE 2009 Chemical Engineering, question number 32. The terminal settling velocity of a 6 millimeter diameter glass sphere with density 2500 kg per meter cube in a viscous Newtonian fluid of density 1500 kg per meter cube is 1000 micrometer per second. If the particle Reynolds number is small and the value of acceleration due to gravity is 9.81 meter per second square, then the viscosity of the liquid in Pascal per second is option A 100, option B 196.2, option C 245.3, and option D 490.5. So this is a question from terminal settling velocity from mechanical operations, and the NPTEL lecture can be found in Unit 4, Lecture 16, Particle Dynamics 1, Mechanical Operations by Professor Shabina Khanam, Department of Chemical Engineering, IIT Roorkee. So here we have been given the terminal settling velocity in the Stokes regime because the particle Reynolds number is very small, which means the particle is settling in Stokes regime. And in Stokes regime, the terminal settling velocity ut can be written as g into dp square into rho p minus rho f by 18 mu f, where dp is the diameter of the particle, rho p rho f are the densities of particle and fluid, mu f is the viscosity of the fluid, and g is the gravity. So let us write the data that is given to us in this question. So in this question, G is given as 9.81 meter per second square. The density of the particle is 2500 kilogram per meter cube and the fluid is 1500 kilogram per meter cube. So rho P is 2500 kilogram per meter cube. Rho F is 1500 kilogram per meter cube. Then the diameter is also given as 6 mm. So that is dP is 6 into 10 raised to minus 3 meter. Also, the terminal settling velocity ut is given as 100 micrometer per second. So that is ut, which is 100 into 10 raised to minus 6 meter per second, or this is 10 raised to minus 4 meter per second. So now we'll substitute all these in our equation, which is ut is equal to g dp square into rho p minus rho f by 18 mu f. So ut, which is 10 raised to minus 4, equal to g 9.81 into dp square, that is 6 into 10 raised to minus 3 the whole square, into rho p minus rho f, that is 2500 minus 1500, the whole by 18 into mu f. So in this we need to find what is this viscosity term mu f. So if we rewrite this, we'll have mu f is equal to 9.81 into 6 into 10 raised to minus 3 the whole square into 2500 minus 1500, that is 1000, by 18 into 10 raised to minus 4. So this is just a simple mathematical operation, multiplication and division. If we do this, we'll get the viscosity mu f is equal to 196.2 Pascal second. So in the options, this is given by option B. So here option B, 196.2 Pascal second is the right answer. Right. So again, this is again a direct application question where you just directly apply the terminal settling velocity, and the only unknown here is the viscosity mu f, and you just substitute all the other values and find the viscosity of the flow. So I hope this section was clear to you. If there are any doubts in any part of this section, you can always ask. But yeah, if there are none, we'll stop here for now. Okay. Fine then, let us stop here for now. And in the next class, we'll be looking into one important topic in mechanical operations, which is the packed bed column. So we'll be looking into equations like Ergun equations, fluidization, incipient fluidization, and so on. And one more thing, next Monday, 30th January, I think. So that will be the last class for mechanical operations and for this section actually, because I think the gate exams start from the first and second, the first weekend, and I think chemical gate is during the second weekend, I think, not sure. But in any case, 30th Jan will be the last class for this series of classes. So the next series of classes might start from after some 2 or 3 months only. Yeah, Feb 11. Yeah. So Feb 11 is the gate exam for chemical engineering. But anyways, Jan 30 will be the last class for us, and there will be a break after that for the gate exams to happen, and a lot of other things are also there. But the next class is the last class again, as I said. Fine, we'll stop here then, and I'll see you guys next Monday. 2024 gate, I'm guessing the classes will start probably from May or June, I feel. So there will be a break of, I think, at least 2 months from Feb. So probably by May or June, the next set of gate classes might start for 2024 gate. Yeah. Okay, fine then. Thank you for joining, and I'll see you next Monday.